Today we are solving LeetCode for median of two sorted arrays. This is a hard problem and we will get to learn these key concepts. This is a hard problem and honestly it looks scary at first because the problem asks us to solve it in order of log m plus n. That means we cannot simply merge both arrays and find the median. But do not worry, in this video we will understand the problem, then solve it using a simple approach, then understand binary search from the basics, and finally use binary search to solve the problem optimally. By the end of this video, you will learn not just the solution but also why binary search works here. So we are given two sorted arrays, nums1, nums2. Their sizes are m and n. So let me delete this. We need to return the median of the two sorted arrays combined. Let us first understand what median means. If the total number of elements is odd, the median is the middle element. For example, 1, 2, 3 is the array. The median is equal to 2. Here the middle element is 2. So the median is 2. Now if the total number of elements is even, the median is average of the middle two elements. So in this case, median will be equal to 2 plus 3 by 2 equals 2.5. Because 2.3 are middle elements and their average is 2.5. Now let us look at the first example where nums1 is equal to 1, 3. Nums1 equal to 1, 3 and nums2 equal to 2. If we merge them, we get 1, 2, 3. So if the total length is 3, which is odd, so the median is the middle element 2. Now the second example, nums1 equal to 1, 2 and nums2 equal to 3, 4. If we merge them, we get 1, 2, 3, 4. So the total length is 4, which is even. So the median is 2 plus 3 divided by 2 equals 2.5. So conceptually the problem is simple. But the challenge is, can we find the median without fully merging both arrays? The first solution that comes to mind is very simple. Since both the arrays are sorted, we can merge them using two pointers. For example, nums1 equal to 1, 3, nums2 equal to 2. We merge them into 1, 2, 3. Then we find the median. For odd length, median equal to middle element. For even length, median equal to average of two middle elements. This solution is correct. But let us look at its complexity. We are going through both arrays, so time complexity is order of m plus n. And if we create a new merged array, space complexity is also of the same order, m plus n. But the problem asks us to solve it in log of m plus n. So we need something faster. And whenever we see log, we should think about binary search. Now before solving this problem optimally, let us quickly understand binary search. Binary search is used when we have a sorted search space. So binary search is used when we have a sorted search space. Suppose we have this sorted array. Suppose we have this sorted array and we want to search for 7. The normal way is to check one by one, but binary search says do not check every element, check the middle element first. The middle element is 5. Now compare 7 with 5. Mid equal, middle element equals 5. And we see that 7 is greater than 5. So the array is sorted. We know that 7 cannot be on the left side of 5. So we can completely ignore the left half. So we only search in 7, 9, 11. Again we check the middle element. The middle element is 9. Now compare 7 with 9. So 7 is less than 9. So now we move to the left side and finally we find 7. This is binary search. At every step, binary search asks, is my answer on the left or is my answer on the right, or have I found the answer? And every time it removes almost half of the search space. That is why binary search is very fast. Now comes the interesting part. In normal binary search, we search for an element. But in this problem, we are not searching for an element. We are searching for the correct partition. Partition means a split. We want to split the combined sorted array into two parts, left half and right half. So let's come back to the problem. Our review of the binary search is over. Merged array can be split into left half and right half. For the median, we need the left half and right half to be balanced. Also, every element on the left side should be smaller than or equal to every element on the right side. So the main condition is max of left half is less than or equal to min of right half. Once we find this correct partition, the median is very easy to calculate. Now take this example. Nums1 equal to 1 comma 3 and nums2 equal to 2. If we merge them, we get 1 comma 2 comma 3. The correct split is 1 comma 2 and partition is. So left side has the smaller half, right side has the larger half. Median is the biggest element on the left side, that is 2. But we do not want to actually merge, so we try to create this split using both arrays. One valid partition is nums1 and nums2. Now the left side is 1 and 2 and the right side is 3. This is correct because max of left side is less than equal to min of right side. So the median is 2. The entire problem is about finding the correct partition efficiently. So let us say we have two arrays. For idea, we have two arrays. One is the smaller and the other one is larger. So let's say A equal to smaller array and B equals larger array. We will always apply binary search on the smaller array. Why? Because it keeps our partition indexes safe and makes the solution simpler. Now suppose we choose a partition in array A. That means we decide how many elements we are taking from A into the left half. Let there be partition A. Now the total number of elements required in the left half is fixed. So the number of elements taken from B will be partition B equals half minus partition A. Here half equals m plus n plus 1 double slash 2. So m and n are the sizes of the nums 1 and nums 2. So why do we add 1? Because it helps us handle odd length cases easily. For odd length, the left half will contain one extra element. For example, in 1 to 3, left half will be 1, 2, right half will be 3. This makes the median equal to the maximum element of the left half. At any partition, we only need 4 values: left A, right A, left B, and right B. So these 4 values we need. So for A, left A equal to element just before partition A, and similarly left B and right B. Now the partition is valid if left A is less than or equal to right B and left B is less than or equal to right A. Why? Because we want every element on the left side to be less than or equal to every element on the right side. Since both arrays are sorted internally, we only need to compare the boundary elements. That is the beauty of the solution. What if the partition is wrong? There are 3 cases. Case 1 is the correct partition. 3 cases are there. So case 1, correct partition. Case 2 is left A is greater than right B. So this means the left side from A has become too big. So we need to move the partition in A to the left. That means I equals partition A minus 1. And finally case 3 is when left B is greater than right A. And that means we need more elements from A. So we move the partition A to the right. Low equal to partition A plus 1. This is exactly binary search. We try a middle element, we try a middle partition, check whether it is correct and then move left or right. Sometimes the partition can be at the very beginning of an array. For example, A, if A is like this, the edge cases. If A is like this, then here there is no left A. So we use left A equal to minus infinity. So in this case, left A equal to minus infinity. Sometimes the partition can be at the very end, for example, like this. So in this case, we will take right A equal to infinity. This makes comparison easy and avoids index errors. Now let us write the pseudocode. So first we should make sure that nums1 is the smaller array. Then we set low equal to 0 and high equal to length of nums1. Then half equals m plus n plus 1, m plus n plus 1 by 2, double slash 2. Now we start running the loop, the binary search loop. While low is less than or equal to high, we update partition 1 and partition 2. Then we set the values of left one, right one, left 2 and right 2. We handle the edge cases there. Now let's come to our first case, that is the correct case. So if left 1 is less than equal to right 2 and left 2 is less than equal to right 1, we know that this is correct and we need to compute the median. So if total length is odd, then we return the last element of the left half. Else we return the average of the middle elements. So this is last element of the left half and this is first element of the right half. We take the average. Now if the second case, left 1 is greater than right 2, we move left. And finally the third case, we move right. So this is our pseudocode. Now we can start writing the code. So first we need to choose the smaller array. Then we set m comma n as the length of the two arrays. Then we initialize low and high equal to 0 comma n. Then we set the value of half m plus n plus 1 double slash 2. Then we start the loop, the binary search loop, while low is less than equal to high. We update the partition values, partition 1 and partition 2. Then we set the value of left 1, right 1, left 2 and right 2. With the edge cases. Then we see if the condition is correct or not. So if it is correct, we compute the median. First we check if the length is odd. If length is odd, we return the last element of the left half. And if it is even, then we return the average of the middle elements. That is last element of the first half and first element of the right half. Now the second condition. So in this case, we will move towards the left by updating the high value, and the final condition where we move towards the right by updating the low value. So this is our code. We can do dry run. So let's dry run one example. Our nums1 is 1 comma 3 and nums2 is 2. So first of all, we make sure that nums1 is the smaller array. So we swap them, and now it becomes a equal to the smaller one and b equal to larger one. Now m equal to 1, n equal to 2, total equal to 3 and half equal to 2. Initially we set low equal to 0 and high equal to 1. Now we calculate partition A. Partition A is low plus high by 2. So partition B will be half minus partition A. So our partition looks like this. Now the four values are left A equal to minus infinity, right A equal to 2, left B equal to 3 and right B equal to plus infinity. Now we check the valid condition, valid partition condition, that is left A less than equal to right B. So left A less than equal to right B and left B less than equal to right B. So it is false. Partition is not correct. It is actually left B is not less than, it is greater than right of A. So left B is greater than right of A. And if you look into the code, then it goes to this statement. So we update low equal to partition A plus 1 equal to 1. Partition A plus 1 equal to 1. Now low equal to 1 and high equal to 1. So again we calculate partition 1 and partition B, partition A and partition B. Now these are the partitions. The four values are left A, right A, left B and right B. If we check the condition, then this is the valid partition. The condition was this. So it is true this time. Total length is odd. So median is max of left A comma left B equals 2. So that so our dry run example works correctly. That means our code should work correctly. We comment it out and run the code. Okay, so these are correct. Before moving further, let's do the time complexity analysis. So time equal to, it will log of min of m comma n, because every time we are reducing it by half, we are applying binary search only on the smaller array. That's why it is with the of the order of log, and because it is small, that's why we take the minimum of m and n. So it satisfies the required complexity of order of log of m plus n, and space complexity is simply constant because no extra array is required by us. Because we are not creating a merged array, we are only using a few variables. Let's now submit this. So okay, so all the test cases passes. So what we have learned In this problem, we learned a very powerful idea. When arrays are sorted, we do not always need to merge them. The simple solution was to merge both arrays and find the median. But the optimized was to find the correct partition. The most important condition was left a less than equal to right b and left b less than equal to right a. Once this condition is true, we know that all elements on the left side are smaller than all elements on the right side. Then median is directly available from the boundary values. For odd total length, median was equal to max of left a comma left b, and for even total length, median was equal to max of left a comma left b plus min of right a comma right b divided by 2. So now finally let's discuss the common mistakes that people make while solving these kind of problems. So first is that applying binary search on the larger array. So always apply binary search on the smaller array, otherwise partition indexes can go out of range. Second is solving the plus 1.5 calculation. We use half equal to m plus n plus 1 double slash 2. This helps us handle odd length cases cleanly.